All right, so what we're going to be looking at here is some problems from section 3.4, I think, which is on the chain rule. And I've sort of written some of these things out, and we're just going to do some computational practice here to make sure that we're feeling good about the chain rule. So the first problem is number 23 right here. I'm just going to move this a little bit. And we're asked to find the derivative. So what I'm noticing here is that I have t times e to the negative t squared. So I am seeing, both a product of t and e, to the negative t squared. I'm seeing a product of those two things and a composite. In this case, that's e to the negative t squared, right? We've got the t squared function, or the negative t squared function, rather, inside the e function, e raised to something function. So I'm going to need to use the product rule and the chain rule. So first of all, the product rule. So dy dt, the derivative of y with respect to t, would be the derivative of the first, which is 1, times e to the negative t squared, plus the first, which is t, times the derivative of e to the negative t squared. And now I need to find that derivative, right, using the chain rule. So this is going to be e to the negative t squared plus t. And now the derivative of e to the negative t squared, remember the derivative of e to the x is e to the x. So the derivative of e to anything else is e to anything else, e to the negative t squared. But now I need to multiply by negative 2t, which is the derivative of negative t squared. So simplifying that a bit, I could write this as e to the negative t squared minus 2t squared, right? Because negative 2t times 2 is, or negative 2t times t, rather, is negative 2t squared, e to the negative t squared. And if I wanted to factor that, I could write it as e to the negative t squared times 1 minus 2t squared, which would then allow me to basically find maybe where the zeros of the derivative are, which would help me perhaps find maxes and mins. Okay, so that's number 23. Number 31. Okay, so what I'm seeing here, right? Important to think about what I'm seeing here. First of all, I am seeing a quotient. However, the denominator is just a constant. So I can use the constant multiple rule. That's pretty important, right? Because dividing by 3 is the same as just multiplying by 1/3. So I can actually keep that out front. Okay, I'm also seeing a composite. I've got basically blob all raised to the second power, right? Blob being that x squared plus 2 over 3. That's my inner function raised to the 2. So I'm going to take the derivative of the squared function and then take the derivative of that blob, which is x squared plus 2. All right, so let's do it. So dy dx would be the derivative of x squared with respect to x squared plus 2 over 3, which is going to be 2 times, I'm just going to leave this as x squared plus 2 over 3, all to the first power. Now I need to multiply by the derivative of the inner function, which is x squared plus 2 over 3. Okay, so this just becomes, if I wanted to write this out, I could say it's 2x squared plus 4 over 3 times this derivative. Well, like I said before, this is the same as writing d dx of 1/3 times x squared plus 2, right? Because dividing by 3 is the same as multiplying by 1/3. So I can just take and say that this has to be equal to 1/3 times the derivative of x squared plus 2, because that's the constant multiple rule, right? If you have a constant out front, you can just pop it outside of the derivative and then multiply. So I know the derivative of x squared plus 2 is 2x. So this is going to be times 2x over 3. And if I wanted to multiply those things out, I could say, well, it's 2x squared plus 4 times 2x all over 9. And then I might factor it and say, well, I could write this as 4x times x squared plus 2 all over 9. And that would be the derivative of this function. So again, if you've got a constant in the denominator, you do not need to use the quotient rule. Although you could, but that would just be more time. Moving on, whoops, I did plus instead of to the next one. Moving on to number 43, which is right here. So again, what am I seeing? I am seeing a composite function, okay? In fact, I'm seeing a double composite. Okay, so outer layer. Outermost layer is the square root. Next layer is the e to the blob plus 5. And the inner layer is that blob, which is negative 3t squared, right? So I've got negative 3t squared, then I have e raised to that, and the plus 5 doesn't really matter because I can just use the sum rule there. And then that's all plugged into the square root function. Okay, so let's take the derivative of this one piece at a time. So let's say dy dt, or the derivative of y with respect to t, or how quickly y is changing with respect to t, is equal to, let's come up here and say that y is equal to e to the negative 3t squared plus 5, all raised to the 1/2 power, right? Because that's what the square root is. So we haven't taken a derivative, we just rewritten it. So now taking the derivative of blob to the 1/2, that should be 1/2 times the blob, which is e to the negative 3t squared plus 5, all raised to the negative 1/2. Now we need to multiply that by the derivative of the inner function, which is e to the negative 3t squared plus 5. Okay, so then we're going to write, I'm going to rewrite this as 1/2 square root e to the negative 3t squared plus 5. I'm just rewriting that, right? Because an exponent of negative 1/2 means 1/2 in the denominator, which is the square root, times this derivative. And the derivative of e to the blob plus 5 would be e to the blob times the derivative of the blob. And of course, the derivative of 5 is just 0. So I'm going to get e to the negative 3t squared plus 0. Well, actually, e to the negative 3t squared times the derivative of negative 3t squared plus 0. So technically, this is all being multiplied, but that 0 is going to drop out. So finally, we know that this negative 3t squared, right? We know that the derivative of negative 3t squared is simply negative 6t. So plugging that in, we should end up with negative 6t e to the negative 3t squared divided by 2 square root e to the negative 3t squared plus 5. And that should just be negative 3t e to the negative 3t squared all over the square root of e to the negative 3t squared plus 5. Okay, so we took the derivative of the root, then the e to the blob plus 5, and then when we took the derivative of the e to the blob, or the e to the negative 3t squared, we had to multiply by negative 6t, which is the derivative of that final layer. Okay. All right, so moving on to some problems that are a little bit more just based on knowledge of the chain rule and looking at graphs. So if we have h of x equals f of g, they want us to find h prime of 1, 2, and 3. So the first thing we need to do is just find h prime of x. And h prime of x, of course, would be f prime of g of x times g prime of x. That's by definition of the chain rule. We take the derivative of the outer function with respect to the inner function, then multiply by the derivative of the inner function with respect to x, and repeat more times if we have more composite functions. So this should be f prime of g of 1 times g prime of 1. So let's see if we can find g of 1. So g of 1 is actually right here, which is 3. So that's going to be f prime of 3 times g prime of 1. And g prime of anything is negative 1 because this has a slope of negative 1. So it's going to be negative 1. F prime of 3 is right here. It would be the slope right here, which is negative 2. So this is going to be negative 2 times negative 1, which is 2. Now, h prime of 2 is going to be f prime of g of 2 times g prime of 2. Let's see if we can make a little distinct make a little line here. So this is going to be f prime of, let's see, g of 2. So here's 2, g of 2 is 2. So it's going to be f prime of 2 times g prime of 2, which is going to be undefined. And the reason it's going to be undefined is that f prime of 2 does not exist, right? No slope right there. So no way that we can find this. So we'll just say that it's undefined or does not exist. Finally, h prime of 3, which should be f prime of g of 3 times g prime of 3. Okay, so f prime of, so what's g of 3? G of 3 is right there, and it's 1 times g prime of 3. So f prime of 1 is right here. It's this slope right here, which is positive 2. And g prime of 3 is, again, negative 1. And so we end up with a slope of negative 2. So we're basically using the chain rule and then just using the graph to find y values and then find slopes. Okay, 67, we've got a problem, and this is just, making sure we understand this rule in a different sort of context here. It's saying y equals k of x has derivative 2 at x equals 1, okay? So they want us to find the derivative of k of 2x at x equals 1/2 and some other things here. So the first thing we need to do is take the derivative here. And so what we have is a composite function. So the derivative should be k prime of 2x, right? Because we're taking the derivative of the outer function with respect to the inner function, then multiply by the derivative of 2x, which is 2. So the derivative of k of 2x should be k prime of 2x times 2. Okay, now we're going to plug in x equals 1/2. So at x equals 1/2, we should get k prime of 1 times 2, because if we plug in 1/2, 2 times 1/2 is 1, of course, so now k prime of 1 times 2. And we know that at x equals 1, k prime is 2, right? Y has derivative 2 at x equals 1, so this should be 2 times 2, which is simply 4. Now for b, it's a similar thing. So we're going to take the derivative of k of x plus 1 at x equals 0. Now I want you to think about this a little bit, because this is kind of interesting. And ask yourself this question. What happens when we shift the graph, or when we add 1 to the input? And the answer is, when you add 1 to the input, it shifts the graph to the left 1. Right? Because now, in order for the function to read you plugging in 1, you need to plug in 0. And in order for the function to think that you're plugging in 10, you have to plug in 9. And so it shifts everything to the left. So basically what we've done here is we have just shifted to the left, and we've shifted our x value to the left as well. So if you take your whole function, shift it to the left, and you choose the place, you're going to shift the place that you're interested in the derivative as well to the left, then we should just expect that the slope is the same, right? It's basically like, okay, well, if k of x looks like this and we find the derivative at 1, then we shift the thing to the left and find the derivative at 0, it should have the same slope. That's basically what we're saying. Okay, but let's check it with some algebra here. And let's say, great, what is the derivative of k of x plus 1? Well, it is k prime of x plus 1 times the derivative of x plus 1. And the derivative of x plus 1, which is the inner function, is simply 1. So it's just times 1. If we plug in 0, we get k prime of 1 times 1. And that's 2 times 1, which is 2, as we expected. Now, finally, let's look at c. We'll take the derivative. We'll get k prime of 1/4 x, but then we need to multiply by 1/4 because that's the chain rule. Derivative of the outside function with respect to the inner function, just leave the inner function alone, then multiply by the derivative of the inner function with respect to x. Now we're going to plug in 4, and this should be k prime of 1 times 1/4. So basically what we're doing is we are, horizontally yoink, stretching this thing out by a factor of 4, and then we're moving over to that point to find the slope. But we should expect the slope, if we're going really stretching this out, we should expect the slope of that point to decrease quite a bit. So this is actually, I actually think it's really interesting to think about the transformations here. And so This should end up being 2 times 1/4, which is 1/2. Okay, so that's kind of interesting. This one is similar where, oh, you know what we're doing? We are squashing this thing in. So if you basically take a point here and then squash everything in, it's going to get steeper at that point, and that's kind of what we're doing there. So pretty cool, actually, little problem to think about in terms of transformations. I really like that one, and maybe I'll put it onto the required list because it's pretty interesting, I think. Okay, finally, we've got a set of problems that deal with these graphs. And these graphs I drew, but they're not really great. So if you want to look at a better picture, you can look at page 139 in the textbook. Of course, this is our textbook right here with the beautiful autumn leaves. And so you can look at it there. But I think I've drawn a picture that at least will allow us to do these problems and think a little bit graphically. So again, we're given a composite function, h of x equals f of g of x. And since we're dealing with derivatives, we might as well go ahead and find h prime. And h prime of x is going to be f prime of g of x times g prime of x. Okay, that's what I know it to be. So h of 0, using my definition here, would simply be f of g of 0. So let's find g of 0 first. So I think this is g of x down here, and that's f of x. So g of 0 is d, which means that we need to find f of d, and f of d is right here, and f of d is actually also d. F of d is d, so f of d is d. H prime of 0 should be equal to f prime of g of 0 times g prime of 0, okay? So let's see, f prime of g of 0. So that's going to be f prime of, remember, g of 0 was right here, it was d. So f prime of d times g prime of 0. That's a 0 right there. And g prime of 0 is 0 because there's a horizontal tangent right there, right? Horizontal tangent. So that means that g prime of 0 should be 0. So this is going to be f prime of d times 0, which is simply 0 because f prime of d, I don't know what it is. It exists. Let's see, f prime of d is some positive number. I don't know what it is, but it's positive. So this is basically some positive number times 0, which again is definitely going to be 0. Okay. 73, they want us to talk about what is going on with h at x equals negative c. So is h positive? Is it negative? Is it increasing? Is it decreasing? So let's see if we can figure that out. So we are curious, what can we say about h of negative c and h prime of negative c? So let's remember that this is f of g of negative c by definition, and this is f prime of g of negative c times g prime of negative c by the chain rule up there. Okay, so what is g of negative c? Well, g of negative c is down here. It's actually negative b. So this would be f of negative b. And f of negative b is 0. So we know that h is 0 at negative c. Now, what about increasing or decreasing? So this is going to be f prime of g of negative c. Remember that g of negative c is right here, and it is negative b. So f prime of negative b times g prime of negative c. Okay, so f prime of negative b. So here is negative b, and f prime is some negative number. I don't know what it is, but it's negative. G prime of negative c, let's see, negative c is right here, is going to be the slope down here, which is some positive number. So all we know is that this is negative, which means that h is decreasing. So we can't say exactly what the derivative is, but we know that it's negative because it's a negative times a positive. And so therefore, it's got to be decreasing. Okay, a couple more to do here, and then we'll call it quits for the chain rule computation. They want us to do the same thing at x equals a. Okay, so remember that h of a is going to be equal to f of g of a. Okay, which is going to be f of, okay, coming back here to our graph, g of a is b. So f of b, and f of b again is right here, which is 0. So we know that this is just 0. And h prime of a should be f prime of g of a times g prime of a. And so that's f prime. Remember, g of a was b. We found that over here, times g prime of a. So let's find f prime of b. So f prime of b is going to be the slope here, which is positive, and g prime of a is going to be the slope here, which is negative. So we should have basically a positive times a negative, which is going to give us a negative, and thus we know that h is decreasing at x equals a. Okay. Finally, h of d and h prime of d have what signs? Okay, so h of d, remember, is just equal to f of g of d, which is equal to f of, let's go back here, g of d is negative d. So f of negative d, and f of negative d is d, and it's definitely positive. So we know that that is positive. H prime of d, of course, is going to be f prime of g of d times g prime of d. And that's going to be f prime, g of d, remember, is negative d times g prime of d. So f prime of negative d is right here, and it's definitely negative. And g prime of d is also negative. So we've basically got a negative times a negative, which is a positive. So we know that both of these things are positive. Okay, so that has been some work with the chain rule, and hopefully that makes you feel good about your computational skills with the chain rule. Okay, let's see here. I gotta quit this record, stop recording. All right, have a good rest of your day. Bye.